Hi, my name is Raghu Govindachari. High-level languages provide much flexibility when compared to assembly programming in terms of code structuring. This helps manage complexity using modularity principles. For example, functions or procedures are one such structuring tool. Variable scoping is another tool for dealing with temporarily local data as well as sharing data across modules and within a module. Finally, data memory may be allocated transiently during runtime. All these high-level constructs need different memory allocation techniques. In this video, we will briefly list these memory schemes, but look at the call stack in detail due to its fundamental nature. We already know that there are two kinds of memory. One is code memory or program memory, where the instructions for a program are stored, and data memory, where the data inputs and data output of those programs are stored. So they are called non-code memory. One can see there are three types of non-code memory, namely stack memory, heap memory, and static or global memory. Stack memory is associated with procedure calls and exceptions or interrupts. The purpose of stack memory is to provide context or environment for a call. The context includes the state of the registers of the hardware and any control flow related information, which is also part of the register, for example, the program counter, etc. In addition, any parameters to be passed to the function are also part of the data stored in the stack, and any local variables within a function is also stored in the stack. The important thing about stack memory is that it is so fundamental that it is supported by the hardware. For example, in the ARM Cortex processor, the stack pointer is a dedicated register, special register pad, which is maintained by the hardware. For example, via push and pop instructions. And there are other instructions which can copy the stack pointer in and out to another register. The frame pointer is another register, which is R11. It's an alias for register R11. We will talk about it in detail later. The second kind of memory is heap memory. It's used for dynamic memory for transient data objects. So in the case of C, data can be allocated using malloc kind of functions and freed. And in the case of C++, the new and delete, or the constructor and destructor when it is when it goes out of scope, and then the STL containers, the template library containers, and of course C++ has exception handling runtime. All these require the heap memory to be used. In general, in embedded systems, especially real-time embedded systems which require predictable response times, it is better to avoid heap memory because implementation of heap memory requires, there is no hardware support, so it has to be implemented in software, and it is part of the runtime of the language. The allocation and deallocation can take variable execution times and hence not preferred in real-time embedded systems. Besides, they use software data structures for housekeeping, which may use locks and hence cannot be used from re-entrant code, such as ISRs or interrupt service routines. Dynamic memory makes memory sharing possible between different pieces of a program. When one module does not need its allocated memory anymore, it simply returns it to the memory allocator to be reused by some other module whenever it needs it. Some examples of data that is placed on the heap include transient data objects, C++ containers, and of course exceptions. The third kind of memory is static or global memory. The static and global are identical in terms of storage, but they differ only in their lexical scope, meaning in the source code of the program, their scope is limited by the compiler, in other words, the namespace. So the variable name is not recognized outside the scope, and therefore it cannot be accessed directly. It can be accessed through aliases such as pointers. That's a different matter altogether. But otherwise, from a storage perspective, they transcend the scope of the usage of the variable wherever it is declared, and uh, its scope is outside. I mean, its lifetime is beyond the scope. That means if the compiler, um, if the variable is declared inside a function, and when the function terminates, while syntactically it cannot be accessed using the name, the actual data is preserved even though that function might have exited. So it cannot be stored in stack. So it is stored in data memory. So such variables, the static and global variables, are determined and allocated by the compiler. It's not supported by the hardware, but it is allocated by the compiler and mapped to .data or .pss memory regions by the linker. So unlike stack, it is not supported by the hardware. Unlike heap, it is not implemented through runtime library, but it is directly managed by the compiler in conjunction with the linker. Now we talked about .data and .pss. .data is basically the region in RAM where all the initialized data will be stored, and .bss is where uninitialized data is stored. Constant data, which is also could be a static or global, constant data can be made read-only and can be located by the linker in ROM area, whereas now variable data in the static or global scope are stored in the RAM. Here onwards, we will focus entirely on stack. So let's understand certain conventions in using stacks or interpreting the stack when we see it inside a debugger. A stack is a data structure that can grow in only one direction, and it is generally used in the convention that it is growing from bottom to top. So when it is empty, it is basically at the bottom, and as you add more and more data on the stack, it grows upwards. But this is only a convention. Now the stack pointer is a variable that tracks the top of the stack, and the bottom of the stack is not tracked dynamically but is fixed and is called the base of the stack. However, implementations of the stack data structure can differ in which direction it grows in terms of the memory address. So while as a concept, data structure, as an abstract data structure, a stack grows upwards as you add more elements. It's like an empty container. As you pour more liquid, it raises the level of the liquid raises. So that is a stack. However, in the actual implementation with respect to the address space, it could be different. Secondly, so basically it could either grow from lower address to the higher address or higher address to the lower address. If the stack pointer moves from lower to higher memory address when an element is added to the stack by the push operation, then the stack is considered as an ascending stack. If it goes from higher to lower memory address, then it is a descending stack. If the stack pointer points to the last filled element of the stack, then the stack is called full stack pointer or full stack. If instead it points to an unfilled location of memory immediately above the last element, then it is an empty stack. Thus, we have four different implementation options for a stack, namely full ascending, full descending, empty ascending, and empty descending. So these capture the two variations on what the stack pointer is pointing to, whether it's pointing to a last pushed element or one above it, or what direction the stack pointer is growing in terms of memory address. So we have four combinations. The ARM Cortex-M architecture implements a full descending stack via its stack pointer and the push and pop operations, meaning the stack pointer grows downwards and it always points to the last pushed element. Now we will look at the concept of a stack. A frame is a set of contiguous locations in the stack, and they are used in the sense either they are actually filled with data or allocated for use, as we will see in some cases, but they are associated with a particular function, a function that is active. Now, many functions can be active at a time because functions may call other functions, and until all the other functions called are returned, this function cannot return. So, this basic functions are getting nested. For each such nested function, there must be a set of locations dedicated in the stack, and that is what is called a stack frame. Now, it's localized region within the stack dedicated for currently active function. And where is it? It is basically, it starts with the return address, and then the frame basically when a function is start, one has to know where to return control back. So the return address is the first thing that is saved on the, and then rest of the information, which includes any registers that have to be saved, any parameters that has to be passed via the stack, any local variables that cannot be stored in registers, and so on. So these are all part of a stack frame for the called function. So there are registers to be preserved because there is only a finite set of registers, and if one function has been using it and it is going to call another function, it doesn't know if the called function will mess with this register or not, so it needs to make sure that it is saved, and the only place it can save is on the stack. If there are in ARM Cortex, normally up to 4 parameters can be passed, 4 word parameters can be passed by the register via the registers. But if there are more parameters for a function, then it can pass the remaining arguments via the stack. Finally, local variables, which again cannot be stored in registers, can be stored on the stack. For example, if you use an array inside a function, and that array is a local variable, and if the size of the array, the number of elements in the array is more than the number of available registers, it will be stored on this. So a stack frame gets created in the prologue of a function. That is, before a function is actually entered into, the calling function is handing over control to the called function. So at that point, just before that handing over control, that is the region called prologue, and that is where any caller preserved registers are saved or on the stack, the return address is saved, and so on. These are part of the prologue. We will see it soon in detail. The stack frame, starting from its bottom, generally contains the return address, previous frame pointer of the calling function, any registers that need to be preserved, function parameters, and these are all part of the prologue. And when it entered the function, the storage of local variables, etc., happens in the body of the function. While the actual contents of the stack frame may vary, the ones outlined before are the most common. Basically, these are the variables, the parameters, and the return address, etc., which are part of a function's stack. Finally, the stack frame gets destroyed during the epilogue of a function. That is, immediately when it is returning control back to the calling function, that is the point called epilogue, and all the used stack elements have to be destroyed. Destroyed in the sense forgotten. So that is part of the epilogue. Now it's important to understand that the stack usage is both for code related information and data related information. For example, the program counter value and the link register value are nothing but pointers to or address of instructions or operations. Therefore, they are code related register. So if you look at the program counter, it is pointing always to the next instruction to be executed. That is where you are currently. And if you look at the link register, it is the saved version of the program counter, that is where you were before entering the function. So the PC and LR are code related registers. PC is where you are and LR is where you were before entering the function. If you look at the data related registers, the stack pointer and frame pointers are related to local data registers. So if you see, the stack pointer is where the local data is and the frame pointer is where the last local data is. So in the sense, the last function's local data is part of the frame pointer and the current function's local data is part of the stack pointer. Now the PC, LR, stack pointer and frame pointer, they all work together along with the parameter passing to create a function machinery. Now we have talked a lot about frame pointers, but it is not necessary that the compiler may use the frame pointer register, which is R11 in the case of Cortex-M. The compiler can instead choose to compute offsets even for past functions which are calling functions, etc. Because the compiler knows it has analyzed the entire calling tree, so it can simply use offsets with respect to the stack pointer, both positive offsets and negative offsets. So as you can see in some compiler generated code, you may not see the R11 register being used. The intent here is that R11 can be used as a scratch register as well. So why waste one register? So compilers optimize by using offset computation as opposed to storing the frame point. Let's look at function prologue, function body, and function epilogue. Prologue sets up the environment for the function. The body implements the function's logic and stores the result to R0. And of course, the part of the body includes the local variables. And epilogue restores the state so that the program can resume from where it left off before calling the function. The purpose of the prologue is to save the previous state of the program by storing values of link register and R11 onto stack, and set up the stack for local variables of the function. Now, the implementation of prologue may differ depending on compiler that is used, but generally this is done by using the push, add, and subtract instructions. So, as I said, if a R11 register is not used, the stack pointer can be manipulated for allocating stack locations for local variables. So if a function has a local variable and if it has to be stored in the stack, simply by adding the stack pointer, the compiler can reserve locations for the local variables, and it can address the local variables using an offset from the incremented stack pointer. So without having to store the frame pointer, it can access the registers or local variables. The last part of the function is the epilogue, and it is used to restore the program state to its initial one before the function call was entered into. This helps in continuing from where it left off without any disruption. What we need to readjust, so for that we need to readjust the stack pointer. This is done by using the frame pointer register as a reference and performing an add or subtract operation. Could also be done with the stack pointer by smart compilers. Once we readjust the stack pointer, we restore the previously saved register by popping them from the stack into the respective registers. For example, popping the link register onto a program counter is one method of returning from a function. Depending on the function type, the pop instruction might be the final instruction of the epilogue. However, it might be that after restoring the register values, we use the branch and exchange instruction for leaving the function. So in the epilogue, we do two things. We basically adjust the stack pointer for any allocated variable to be freed, and then pop the return address onto the program counter. Another alternative way is to use the branch and exchange instruction. A small distinction needs to be made among functions. There are leaf functions and non-leaf functions. A leaf function is a function that doesn't call other functions directly or indirectly. Indirectly meaning using function pointers. So basically the function is a leaf terminal point, and once it returns, there is nothing that it has called to be cleaned up. So there is a difference between how leaf functions are managing the stack versus the non-leaf functions. A non-leaf function, as opposed to a leaf function, may be invoking other functions. Therefore, it needs to do more work in order to preserve. A leaf function does not call another function. Therefore, it doesn't have to worry about its registers being messed up, or return address has to be stored, and so on. Whereas the non-leaf function cannot assume that. So basically they differ in the way the prologues and epilogues are implemented. The non-leaf function saves more registers onto the stack. For example, because it calls another function, the link register holding its return address may have to be preserved before calling the function. Similarly, any registers that needs to be, they are called caller saved registers as per the ARM procedure calling conventions. Now, if you look at the example here, a prologue of a non-leaf function, it basically, this is the start of the prologue, saving the frame pointer and link register onto the stack and so on. If you see the prologue of a leaf function, it is also saving the frame pointer, but it may not save other registers. Okay. An epilogue of a leaf function, you can see that it restores the frame pointer and basically transfers control to the calling function using the branch and exchange instruction, and using the address saved previously in the link register. Whereas in the case of a non-leaf function, the program counter still needs to be saved because, so basically it is popping from the stack to the program counter. So there is a difference between how leaf function is returning control and a non-leaf function is returning control. So far we have looked at the mechanism of a stack in terms of how it is allocated, what are the limits, what is the top, which direction it grows, and then which hardware registers are used for managing the stack, and which instructions are used for transferring control across functions and managing the stack in terms of push and pop, add and subtract and so on. Now let's look at a phenomenon which is very likely called stack overflow. If you look at the figure, we know that there are three types of memory, and they are all part of the same physical memory, which is RAM. So there is heap, there is static and global, and then there is the stack. Typically, the stack is a sandwich between the heap memory and the globals. The idea is that this is basically growing downwards. Now, the number of variables for static and global is known a priori at the time of compilation and linking. So, exact need for how many RAM locations are needed is known, and therefore it is first allocated at the lowest address of the stack, lowest possible available address of the stack. Of course, the lowest address will have the vector table and so on. And after that, the globals and the static data are stored because it is the size of it is known. The second area is used for stack, and heap is for dynamic memory, and we don't know how much the program will require. So it is at the top of the stack. So maximum range of locations is available for the heap. The stack itself is being sandwiched. One needs to know the size of the stack, and it is not very easy to determine the exact size of a stack required for a program. And if you underestimate the stack size, and if the stack grows beyond the stack limit, then you result in what is called a stack overflow. So here is the stack. This is the region of stack allocated by the initialization routine. So here is the stack base, and here is the stack limit. And if the stack pointer moves beyond the limit, the hardware does not check that, and it starts treating the area which is reserved for globals or static as if they are stack area, which means it's definitely going to corrupt or overwrite some of the static or global data. Why this happens? There can be many causes. So it could be because of underestimation, or yeah, of course it is always because of underestimation. And then there is a large local array, which is not a good design idea because it consumes a lot of stack space. And there could be composite parameters passed by value. So which means like an array is being passed as a parameter. Just like array as a local variable, array as a parameter will use the stack. Or it could be a very complex structure. For example, a complete message from a protocol interface could be consisting of an array of structures and structure of arrays and so on. So if one tries to pass them as a copy on the stack, it's going to consume a lot of stack area. So it is also possible that program bugs can cause stack overflow, but most likely the stack overflow is because of underestimation. Why is it hard to estimate the size of the stack? Because of nested function calls and recursive functions. And therefore, the stack adds up as you nest them. And recursion is a sure shot way of nesting that is compounded by large arrays stored in the large arrays as local variables. So nesting in combination with large arrays or recursion in combination with large local variables can worsen the situation. Then there could be indirect function calls and interrupts and exceptions. And interrupts and exceptions are not in our control, not predictable, and not predictable by the function's logic. Therefore, one has to budget for every single function can be interrupted by an interrupt or an exception. thereby one needs to add the local variable usage of the interrupt service routine to the stack estimations. In systems where there is on operating system, there are two stacks at least used because of protection reasons. So there is the thread stack and the handler stack in the case of ARM Cortex at the hardware level, and user stack and system stack at the software level. And so one needs to estimate. We don't know which stack is used when. Of course, we know, but then how much nesting happens on which stack. So one has to now estimate for two stacks instead of one. Runtime libraries may also allocate memory on the stack, and we don't know because we just use them as black boxes. So it is difficult to a priori know the stack usage. And then, of course, compiler optimizations. For example, compiler may actually uh, unfold data on the stack as opposed to reusing the register and so on. So it could cause stack growth. So the stack memory has to be allocated statically by the programmer. The stack usually grows downwards in memory, and if the memory area allocated for the stack is not large enough, it's going to overflow into the global data. Many microcontrollers implement multiple stacks, and therefore one has to calculate for both these stacks. In the previous slide, we saw that stack can overflow, and one needs to estimate it, and it's not easy to estimate. So, what are the solutions? Practical. Uh, when designing an application, the stack size requirement is one factor that needs to be considered, and you need a method of determining the amount of stack that you need. Even if you would allocate the entire remaining RAM for stack usage, you still cannot be sure it will be enough because of interrupts and so on. One obvious approach is to test the system under various conditions and look at the trace of the stack usage and use that for subsequent production runs. Now, again, it is not practical because you have to run the test cases under realistic conditions, and it may take a lot of time and effort. During these tests, you will need a method for finding out how much stack has been used. So even the first thing is you run test, but one needs to have information about the stack usage. How do you collect that information? That's what we are talking here. One way of calculating the stack depth is to use the address of the current stack pointer. This can be done by taking the address of a function's argument or a local variable, the first argument or first local variable as a reference, and the current stack pointer, and the difference between them is the stack size used by that function. So that's basically so if you take the main, and so you take argc as a parameter as a reference, so it is in the stack, and you note that down as high stack, and then identify the deepest leaf level function, and again look at the pointer to the array local variable here, and so the difference between this is the lowest possible stack address, lowest in the sense of memory address. So the difference between the highest and the lowest is the maximum stack size. So it should be noted that the results obtained with this method do not take into account stack usage by interrupt service function. Secondly, it is also assuming that the stack is used for all arguments and local variables. However, registers could be used instead, so it is not realistic in some sense. The Problem here is that one needs to know what is the deepest leaf level function and then instrument it. An alternative approach is to periodically sample the stack pointer without any knowledge about the code structure. Whatever is the deepest function, we don't know, but keep track of the stack pointer. How do you do that? Using a high frequency sampling method, such as a timer. And so every few milliseconds, the stack pointer can be uh, tracked, and then the highest value of the stack pointer is saved. And eventually, when you finish the execution of the test run, that number gives you the maximum stack growth, and therefore the stack size can be computed. But still, it can miss short interrupt service routines. So unlike the previous method, this includes interrupt service routines, but it can miss very fast interrupts because the timer interrupt may not have executed. So it is probably smaller than the timer interval. An interrupt may come and that may be missed. The picture here shows the heap stack under static global variables, but in addition, there is a guard zone. The idea of a guard zone is to protect, in the case of stack overflow, protect the global variables and stack variables being overwritten. The assumption here, of course, is that the stack overflow amount is smaller than the guard number of RAM locations. Now, if it's still possible that the stack can overflow beyond the guard region, therefore the guard region has to be sufficiently large to prevent any stack overflow affecting the global variable. It does not help basically to just have a guard region without knowing whether actually the guard region was disturbed by the stack overflow. Whether stack overflow happened or not, one needs to know. So in order to do that, it is typical to fill the guard region with a predetermined pattern, which is not typical for any program to use. So those are called guard fill patterns. And then after a test run, one looks at the guard region and then see if any of these patterns are intact for the entire guard region or it has been erased, overwritten for some part of the guard region. Once we know that, we know how much the stack overflow has happened and we can increase the stack allocation by that much. That is one step. So a guard zone is a region of memory between the stack and the globals, and it should be reasonably large for simple overflows. Now it's the pattern filling is assumed to be unique, and it's not. It's a rare coincidence that actual code which overflows uses this pattern. Then there is another method for tracking the stack usage. This is basically filling a pattern, again unique pattern, for the entire stack. In contrast to filling the guard region, you fill the stack, initialize the stack with a unique pattern such as CD, CD, CD. The idea is that after execution, you can check how many of those CD locations are still having CD, which means we have overestimated the stack, and the entire stack is not used, and therefore one can look for the CD patterns and then decrease the stack allocation by that much. So there are two things. The guard region with the fill pattern is used for determining how much of an overflow has happened. The stack region with a pre-fill pattern can be used to analyze how much of underflow has happened, which means you can optimize the stack size accordingly. This is typically used by debuggers. We can see in one live session that we will show. Let's take an example to illustrate some of the concepts that we have been discussing so far. So here is a function, here is a program, the main function, and then there are three other functions. The main function calls the function foo, and foo in turn calls bar, and bar in turn calls foo bar, and foo bar is a leaf level function. So the first concept is that these is the only leaf level function, and then rest of the functions including main are non-leaf level functions. The second point we will notice is that function foo is allocating a local variable called ARR, an array of integers. So we will see how that is pushed onto the stack. Let's now compile this and load it. Okay, so so the compiler has been set up not to straight away go to the entry point of main, but start at the startup code. So just to show, at the top of the or the lowest memory address, we have this symbol called cstack $limit. So this is provided by the linker, and this is basically at the zeroth location or the first offset of the vector table. And as we know from the microprocessor uh, module, that this is loaded onto the main stack pointer. So this value is loaded onto the stack pointer here, which is shown as 408 hexa. Now if you recall, 400 would be 1K, and so it has allocated 1K plus 8 bytes. We will discuss why that extra 8 byte is. So now let us directly enter the main. So we'll run to cursor. Now you can see that the stack pointer is pointing to address 400. If you see here, this is a memory location. You can see beyond 408, other higher addresses, it is filled with patterns CD, CD, CD. At 404 and 408, there are two beyond 400, 8 bytes have been filled with the pattern A5, ED, F5, FE. So basically these 8 bytes is the God region provided by this debugger. And beyond that is the stack. Now it has already put something on the stack as we ran through the as we ran through the startup code and entered main. So there is at least something first. So stack pointer is now pointing to the first location, filled location, which is 400. Let us go forward and see what this code does here. So there are various initializations that are being done corresponding to this local variable, global variable initialization in the source code. IA equal to 1, IB equal to 1. Corresponding registers are initialized. And then we come to the calling of function foo. So let's run up to here. As we came here, the stack pointer is decremented. Basically, it is growing downwards, and you can see it has pushed additional information here. Now it's going to enter. This is part of the prologue before we called foo. You see that it has not actually pushed anything onto the stack in terms of in terms of any registers to be saved, because compiler has analyzed and it has determined that there is nothing to save. Let's step forward. Here, basically it is pushing these registers because foo is going to call other functions, and it is using these, it wants to uh, process registers. So it is pushing that. Let's see after the push. So there are about, so there are one, and then R3, R4, R5. So four registers of four words basically has been pushed. So the stack pointer has been decremented by that much amount. Now here is the interesting thing. There is a subtract instruction with the stack pointer as the operand, and it is subtracting it by hex38, which happens to be 40 bytes. So 40 entries, 40 bytes. The stack pointer is decremented by 40 bytes. Remember, we have an array declaration of 10 integers in the function foo, and the data is allocated on the stack. So 40 bytes of data to be allocated here is done by using the stack pointer, by actually decrementing the stack pointer. Remember, stack pointer is growing downwards. So we are growing the stack by reserving 40 bytes, and that is done by manipulating the stack pointer. We are not using the frame pointer here. So that is the next point. And so this is into the body of the function foo. So as we go forward, it is doing whatever computations that are there. Now it is going to enter the call for the bar. So if you see in the source code, it is showing the source code statement C equal to bar of A comma B. And in the prologue here, before calling bar, it is doing a couple of register copying and then a branch and link. So we have entered the bar function, and it is again the bar function has pushed certain registers onto the stack and started manipulating the stack for the register information, and it is in now going to call foo bar. So again it is entering a prologue mode. So far we have only been seeing prologue because the function is not unwinded yet. So main was calling foo, foo was calling bar, and bar is calling foo bar. So you're seeing prologues of this. Now remember, foo bar is a leaf level function. So it will not have any, it will have a different strategy. So basically we have entered foo bar and there is a computation here. You don't see any pushes preserving the registers here in contrast to the non-leaf functions. So here it is directly loading the data and incrementing that counter and so on. And finally it will have to return. Now see the way it is returning here. It is a branch branch and exchange using the link register. It is returning back to bar. So this you watch the stack pointer now increasing in value. Basically, it means that stack is shrinking. Here we are actually in the epilogue after on the return statement of we are yet to do it. So we just returned from foo bar, and so we are now in the return stage of bar. So as an epilogue, you see that it is popping the so it is going to return from bar back to foo, which called it. Here you can see how it is using the pop instruction instead of a bx instruction to load the program counter to the return address. You see the program counter is now A0 here, and we will do the pop and then see. So note down the program counter, it is A0, stack pointer is 3A0 hexa after the pop instruction. So unlike branch and bx instruction, it is using the pop instruction here. This is a non-leaf epilogue. So it has done the popping. So it has increased the program counter is modified to point to the next instruction after the bar in the source code here. And the stack pointer has grown because of the pop. So if you see, it's further doing a pop for returning from foo back to main. So we saw leaf level function not pushing any registers because it doesn't have to save them, and not in the epilogue, that is in the prologue, and in the epilogue it is actually not returning by popping, but it is returning by a branch and bx instruction. As opposed to that, the non-leaf level functions are popping, and before when they in the prologue they were pushing, and in the epilogue they were popping. So that basically concludes the execution of this function. And to summarize, we saw that stack limit was set by the compiler initially as part of the main stack pointer, and it had allocated 8 bytes extra as guard byte and filled them with a pattern, unique pattern A5, ED, F5, FE, and that can be used for stack analysis. And the stack itself was initialized to pattern CD, and it could be used for any under usage detection if need be. The other thing is that we saw that functions or leaf level functions and non-leaf level functions, and non-leaf level function prologues and epilogues differed from the prologue and epilogue of the leaf level function foobar. We also saw that a local variable, which is an array of 10 integers, was pushed onto the stack, and this allocation was done by basically subtracting from the stack pointer. Basically, it is moving the stack pointer further up the stack down the memory address. So to summarize the video, stack is a very important data structure supported by the hardware. It extends the limited register resources for storing data and control context. It is heavily used by the compiler for managing control flows across functions. It's also used for exception handling. In ARM, Cortex-M stack is implemented as full descending convention. Main stack limit is set up by the linker script at address 0000 and is automatically copied onto the stack pointer. A stack frame is the complete subset of stack area dedicated to an active function. Register R11 is recommended for use as frame pointer for the current function. Stack size estimation is hard and can potentially overflow. Stack pointer can be traced during execution by a high-frequency timer interrupt. Guard regions and predefined fill patterns are used by debuggers to detect stack overflows. From a programming point of view, it's a good idea to avoid large local variables and avoid deep recursion. In fact, embedded systems, it's not a good idea to have recursions at all. And we know that all recursive programs can be rewritten as iterative programs.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today